Okie doke, welcome back. So in week 3, part 2, we're going to continue with our review of things that we covered during the first 2 weeks worth of lectures, along with some examples. We're also going to introduce modules of code that are packages, typically of functions, perhaps of classes, stored together in a file, and you can do what's called importing the facilities from that module to use them within your own program. All right, and we'll see that at the end of this material. So at the end of part 1, last time, we talked about 2 different forms of loops, namely the for loop for stepping through the items in an iterable, and a while loop for stepping through statements within the loop until some condition, we hope, eventually becomes false. Of course, as I accidentally demonstrated for the second time, if you forget to update your loop variable so that the condition does eventually become false, you end up creating an infinite loop. So while loops are risky in that way. And we reviewed briefly the equality, inequality, relational, and identity operators, as well as the logical not, and or that you can use in Boolean expressions. Now we're going to take a look at the if decision. If you need to make a decision about whether to do some chunk of code or not, or perhaps whether to do one chunk of code versus another chunk of code, then you can use an if. Following the if is some Boolean expression, that is, some expression that produces a value that can be interpreted as true or false. If that Boolean expression is true, then the indented statements within the block underneath the if are executed. So a decision has to have exactly one if. If you don't have an if, you're not making a decision. Following the if, optionally, you're allowed but not required to have a sequence of elif chunks. Elif is simply an abbreviation for else if, and each elif has its own Boolean expression. So the meaning here is if this first Boolean expression is true, we're going to perform this collection of statements. Otherwise, if the first Boolean expression was not true, we'll examine this Boolean expression, and if it's true, we'll perform this block of statements. And we may have a sequence of these elifs. So I said otherwise, but otherwise is, logically equivalent to else if. So if this Boolean expression is true, do these statements. Else if this Boolean expression is true, do these statements. Else if some other Boolean expression is true, do some statements, etc., etc., etc. And then finally, optionally, at the bottom, you're allowed to have at most one else part. All right. To get input from the user, Python provides an input function, and you give the input function an argument. Are you a... Naturally, I picked something I can't spell. Gemini. Now I'm embarrassed. Let's pretend that I've spelled Gemini correctly. Maybe I accidentally did. And what the input function does is to display that prompt and wait for the user to type some input. I'm going to type yes because I happen to be one. And now the variable answer is set up as a reference to that string of input that I typed, and I can process that using an if, elif, else kind of decision. If you need to, you can convert the string the user typed. Here's an example. You can convert the string the user typed into a number that you can then use for computations. You can use all of the base data type names as conversion function names. So here I'm converting a float value into a str. Next, I'm converting a float value into an int. That's always accomplished by just truncating the fraction part. So int of 4.567 is just 4. Int of true is always 1. Int of false is 0. Converting an int to a float works assuming that that int is within the range of possible values that will fit into a float. If the integer value is too large, then that float conversion will produce an overflow exception. All right, here we're converting a string to a float. And in terms of Boolean conversions, the rule is that any kind of 0 or the empty string converts to false. Any non-zero value or any string that's not empty converts to true. Now, when you do a conversion, you suffer the risk of raising an exception if the conversion is not possible. And we had previously seen an example like this where, let's suppose we ask the user to enter their age, and they type text, 15 or 37 or whatever it might be. The float conversion function is not smart enough to be able to convert that into a floating point value. So you get something called a value error exception, and ordinarily that would cause your program to crash. However, if you fear that the conversion might fail, but you don't want your program to crash, then you can set up a block of statements that you fear might produce an exception in a try. Okay, this is a try block. And below the try, at the same level as the try, you can use except to collect and deal with any kind of exception that may have occurred in the statements within the try block. In this case, we are trying to convert some bogus value. I'm going to say try to convert (1324.4) hello to a float. Now that fails. Everything is fine in the 132.4, but hello definitely won't be able to be converted correctly. So that is going to cause an exception, and I'm going to set x to minus 1.0, which we'll assume is some bogus value that I can test for. All right, I do not see any error occur on my screen here, because if an exception occurred, it was caught by the except, and I see that x is minus 1. So evidently an exception did occur and was caught. Here I've been typing examples interactively at my shell, but most of the time you want to put your code into a file whose name typically ends in .py, so that you can then execute that program file at any time you wish in the future. And for most small to medium-sized programs, at some level for all programs, the simplest methodology for putting the program together is to first gather some input from somewhere. Now that input might be hardwired into the program, that is just typed as part of the program itself. Let me create a new file here. Okay, and let me shrink this down to a manageable size. I'm going to call this thing example.py. And this is, the outline of our program. It's going to be gather some input data, process the data in some way, produce some meaningful output for a user. Okay, so input, process, output is a top-level outline of virtually any kind of program. This style of programming is very often referred to as top-down programming. What we mean by that is this top-level, this high-level outline is really very self-explanatory. Get some input, process the information, produce some output. Very easy to remember, very simple. You can just use that as the outline for almost any kind of program that you want. Now, gathering some input, that actually may involve a series of steps. That may involve opening a file. It may involve asking the user for some input, and after you have opened the file or asked the user for some input, you might additionally need to do some kind of conversion so the data is in the format that you need in order to do processing. So there may be a sequence of steps involved in getting the input, and you can therefore break this first step, gather some input data, down into a sequence of substeps. Also, once you have got the data read in from wherever you're getting it from and organized in whatever fashion you need it in, then processing the data may also involve some number of steps. Let's suppose that you have some data about patients' heights, weights, blood pressure, and you would like to compute means, standard deviations, and those kinds of statistics. Well, you have the data. Now computing the mean is going to be a brief little algorithm. Computing the standard deviation is going to be a brief little algorithm. And so this processing you can think of as being a sequence of steps. Then producing meaningful output may furthermore require a sequence of steps. Maybe you want to produce a table of output for patients' weights, a table of output for patients' heights, a table of output for the ratio of weight to height, a table of output for blood pressures. Each of those is a sequence of steps, and perhaps each of the steps in each of these three major sections is a simple Python statement, or perhaps each step might be more complex, and it may make sense to call a function for some of these steps. We'll just arbitrarily call them, function A, function B, function C. So you're breaking the major steps down into substeps. Each of those substeps might be a function call. Within the function, you're further going to break things down into steps. So you have this hierarchy of steps, organized starting from the topmost simple level, input, processing, output, and you're working your way down until you can directly, in simple Python code, solve each sub problem. All right, well, that got relatively long. I apologize. But that's the idea of top-down programming. You start out with this input, process, output, organization, and then you have to think about, well, how do I get the input? How do I organize the input? How do I convert the input? Once you've got the input, you think about, well, now how do I process the input? And once you've done the processing, you think, okay, now what output do I need to produce? All right. We looked at this simple user age program. This is an example of a program that gets input from the user. In particular, it asks the user for an age and reads in the age and then tests to see whether what the user typed in makes sense. And in this case, we needed to use a while loop because users are notoriously error prone. And so we keep asking the user over and over and over again until they type some value that makes sense. And then we're not really doing any processing, having read in that value. We're just producing some output telling the user, okay, I got your age is whatever it is. So a function is a unit of code that you can use as a substep in one of these overall steps. And you can sort of think of a function also as following this input, processing, output structure, except that in the case of a function, the arguments that you pass into the function are in some sense the input to the function. Okay, it's not the same as input from a file or input from a terminal, a user's keyboard, but it is input in some sense that the argument provides some information for the function to process. Now, the processing may involve performing some kind of computation. It may be more complicated than that. It may involve decisions, it may involve loops, and so on. And the output, in a typical case, is a value that is returned through a return statement back to wherever the function was called. So here we have this F to C function that receives a Fahrenheit temperature as its argument. That's the input to the function. It processes that argument by computing 5/9 times that argument minus 32. And then that value, the result of that value, is returned back to the point where the function was called. And so here I'm calling F to C, passing in the value of the t variable, which is 43.2. I compute the Celsius equivalent and return that value, so that return value becomes available to be passed to the print function. And then the print function prints out T Fahrenheit is whatever that number is, Celsius. It is possible, by the way, for a function to directly return, sorry, I misspoke. It is possible for a function to directly produce output. So I can say something like this, define F to print C, some temperature, and rather than returning the value, I can say print 5/9 times the quantity F minus 32. All right, so this function, if I say F to print C of, well, let's use 212, which should be, 212, which should be exactly 100 degrees Celsius. And it is. This time, the function did not return the value. The function directly used the print function to display the value to the user screen. Okay, so each step in a complicated process in your code, in your program, can be a function call, and we refer to this step-by-step decomposition of the overall organization into a sequence of steps, many of which are functions, as functional decomposition to get your program to run. Here are a couple more examples of a function, or of functions, I should say. We have min of 2. This function, min of 2, takes two arguments, which we're calling a and b. I could have called them x and y, or, abracadabra and giraffe, whatever. And what I'm doing here is I'm testing whether a is less than b. If a is less than b, then the minimum is the value of a, so I'll return the value of a. Otherwise, the minimum must be the value of b. Okay. I told you I forgot the colon on the else. Let's try this again. Define min of 2ab. If a is less than b, return a, else colon, return b. And now if I ask for min of 2 of 12 and 1.234, this works fine. I can compare an integer to a floating point number. The minimum is going to be 1234. So because 12 less than 1.234 is going to be false, I'm going to drop into the else here and return 1.234. Now, you can compare strings, recall, as well. And so if I compare hello with a capital H and hello with a lowercase h, I get back hello with a capital H. Now, why is that? Remember, I hope you remember, I will mention it again, that in the ASCII character set, all of the uppercase letters come ahead of all of the lowercase letters. So in terms of how these things are stored in the machine, capital H has a lesser value in terms of its bit pattern than lowercase h. And so hello with a capital H is lexicographically in the system's character set earlier in the alphabet than hello with a little h. All right. Now, this next function is called min of 3. And this is also an example of the idea of functional decomposition or top-down programming. When you are trying to implement a function like min of 3, now min of 3 takes 3 arguments, a, b, and c. How can I get the minimum of 3 arguments, a, b, and c? If I just think of that without reference to anything that I already know, it seems kind of complicated, because I could test whether if a is less than b and b is less than c, then a is the least one. But if b is less than a and b is less than c, then b is the minimum one. That seems like I'm going to have a big giant if, elif, else inside here. But actually, let me think about it in terms of this min of 2 function that I already have. Because isn't it true that if I return the min of 2 of a with the min of 2 of b and c, all right, here I have nested function calls. That means that the inner function gets called first. Even if you haven't got much programming experience, you would probably expect that just from what mathematical training you may have. So the inner min of 2 is called first. We get back the minimum of b or c. Then we ask for the minimum of a with respect to b or c. And that must be the minimum of a and b and c. So by making use of a function that I already know about, I can reduce the implementation of this min of 3 function to a single return statement with nested function calls. All right, so now I can say min of 3, 123, 432, 12, and I get back 12. Or I can ask for min of 3, hi, hello, hey, and I'm going to get back, well, let's see. So I comes after E, Y comes after L, so the minimum of these is going to be hello. All right? Okay. We also looked in the previous section at using the with keyword to allow us to open a file that we can use within an indented block of code. The advantage of using with as opposed to just using a simple assignment to a variable is that closing of that input file is automatic. So later, if I open that file again using another with open statement, the file will start over from the beginning and I can reread the file from the beginning again. Here we are using a for loop because this input file is an iterable. We're using a for loop to say for each line in the input file. Now, as you will have discovered in a homework, when you use a for loop on fn this way, the Newline character at the end of each line is not stripped off the way that the input function does strip off the enter key that the user types. So if we have a string that looks like inster is hello world Newline, then we typically want to get rid of that Newline character so that we can do some processing of that line excluding the Newline character. And a simple way to do that, as we saw, is to ask for inster up to but not including the last character. All right, the last character here is the Newline character, represented as \n. And so now I get the string excluding the Newline. And I can simply reassign the variable name inster to get the result of inster with that last character stripped off. All right? Then I can, for example, as we saw, split the line into a list of words. This split example is using commas. I might want to do a split involving a space character. Well, actually, I've created a little bit of a mess for myself. I guess we can do that. We can say m gets inster.split at comma, and now m is going to be a list of two strs. The first is hello. The second is space world. Okay, and then I can analyze these individual strings within this list of strings. Okay, so that is an example, a reminder of using with open, which avoids the necessity of remembering to do close yourself, and also a review of how to get rid of the Newline character at the end of each input line, and also how to split up the line into separate pieces. Here, by the way, are some special characters that you should know about. The most common one you're going to be dealing with is the Newline character at the end of each line. All right, that's represented as \n. You might occasionally encounter a carriage return character. Now, what's the difference between a Newline and a carriage return? Well, technically speaking, the Newline character is also called, all right, so this character is called the Newline. It's also the line feed character. And now here I'm having to think back to my youth, my teenage years. My mother and my friend's mother forced us to go to a typing class in 5th grade during the summer, which was horrific. Good heavens, in 5th grade, in the summer we're taking typing. Turned out to be one of the most useful courses I ever took. And we were using old style typewriters back then. And when you manually return the carriage, first the carriage would go back to the beginning of the line, and then the roller would move forward by one line. So you may have seen in documentation, and perhaps not understood what it meant, this notation CRLF, which is described as being the end of each line, especially in a Windows environment. CRLF stands for Carriage Return Line Feed, and it means to move the cursor back to the beginning of the current line and then drop down one line to the beginning of the next line down. And in a Windows file, this is literally represented as Carriage Return Line Feed. Those two characters. In Unix systems, Linux systems, Mac systems, the carriage return is left out, and instead we just have a Newline character in these files. And when the Newline character is displayed onto a terminal, the display logic understands that that really means to do a carriage return followed by a Newline. So the carriage return is left out and considered to be redundant. All right. So we have both the Newline character, which is also called the line feed character, and sometimes you'll encounter a carriage return character. The horizontal tab character is \T, and let's see what that does. I'm going to just hit Control-C here to kill this off. If I say S gets this \T is \T \T test. Each of these \T's is a horizontal tab. And in the interactive shell, when I display S, what I'm getting is the internal representation of S within the program. It's only when I call a function like print to display S in human readable form that I see each of these tabs processed. So the default tab stop in most environments is 8 characters. So what I have in this environment is THIS followed by 1, 2, 3, 4 more spaces. And notice that I didn't highlight one space at a time because the tab jumped over by those 4 spaces. Then I have is followed by 6 spaces worth of a tab, and then followed by 7 spaces worth of a tab, and finally I have test. Okay. And there are some other individual characters represented using the / notation as well. If I want to store a single quote inside of a single quoted string, I can use / single quote to represent a literal single quote inside of a single quoted string. Similarly, I can use backslash double quote to represent a double quote character. I can use backslash backslash to represent a single backslash character. Let me show you what I mean. This is a new line. But this is a backslash followed by n. Actually, I wanted to put a variable for that to refer to that. So S1. This is a new line. Okay, so those two characters, backslash n, represent a new line. And following that new line on the next line down, I'm saying, but this is a backslash followed by n. So backslash backslash is a literal backslash, and n is just n. The representation of that I display by just typing S1 at the shell doesn't seem very interesting. But if I say print S1, I will see, okay, this is a new line. Well, the new line character caused the cursor to drop down to the beginning of the next line. But this is a backslash followed by n. The pair of backslashes is displayed as a single backslash, and then the n is just displayed as n. Okay, so those are some of the so-called escaped characters that you should know about when you're doing Python. Okay, so that gets us to the conclusion of our review. Base data types, arithmetic, relational and equality and logical operators, loops, decisions, lists, functions, and then this top-down organization of a program, starting from the very highest level organization, which is get some input, process the information, produce some output. The final thing we're going to take a look at here, which is new, is the idea of modules of code that you can pull into your program to provide extended capabilities that are not directly built into Python itself. You pull in a module by doing what's called an import of that module. And one of the most common modules to import is the math module. So let's do that in this example program. I'm going to save this. I'm going to say File, Save As, and I'll call this example.py. Okay, so in the notes here, this is illustrated interactively, but I want to illustrate it within a program. I'm going to actually erase these comments here, and let's just try displaying the square root of 2. Okay, square root is a math function. We ought to be able to find out what the square root of 2 is. It's going to be 1.414 something. So let me save this by pressing Control S, and then we'll run it by pressing, by pressing F5. Okay, recall that run module, the shortcut for that is F5. And I get a name error. I get told that the name square root is not defined. And okay, well, so there we are. So the len function is defined, the print function is defined, but the square root function is not defined right in Python itself. It turns out that in order to make use of the square root function, I have to import, or I can, import the math module. Now, what this import statement does is to go out looking for a file whose name is math.py and to pull in a copy of that file. And it turns out what that file contains is a large number of definitions of standard mathematical functions. To use a function from the math module, I need to prefix the square root function call with the name of the module that contains the square root function. All right, so there's my modification. I'm importing math, and then I'm saying to print math dot square root of 2. And now it works, 1.414, etc. Okay, now I might very well get tired of having to type out math dot for every math function that I want to call. I've got square root, I've got e to the x, natural log of x, sine, cosine, tangent, all kinds of standard math functions that might occur to you are contained within this math module. The module name math is not too bad. It's only 4 characters wide, but some module names are very long, and you definitely don't want to have to type these very long module names in order to use a facility from them. So what I can do is I can say import math as, and then provide some abbreviation. Use M as the abbreviated module name. And now instead of saying math.square root, I can just say m.square root. And I can also say things like m.cosine of 2, print m.log of 2. Maybe I should put some text in here. So that I have descriptions of what is being displayed for each one of these things. Okay, so I'm just doing some cutting and pasting, and then I'll edit. All right, so I'll save this with Control S and press F5. And there we are. So I have the square root of 2, the cosine of 2, and the natural log of 2. Okay, now, perhaps I don't want in my program to use all of the facilities that are available from this math module. It turns out that I can import an individual function from the math module by just saying from math import this one particular function. So let's try that next. We'll say from math import, and let me do square root. Now I don't have to say m dot at all. And in fact, these other ones here, cosine and log, these will not be available because I have not explicitly imported these two functions. So when I save and run this program, I will get the square root of 2, but then I'm going to get an exception because cosine is not found. The program will die, and I won't see anything at all about log because the program died before we got to log. So save the program with Control S, run it with F5. Hey, okay. Well, I thought I pressed Control S, but sometimes I miss. So source must be saved. Okay to save, I'll say okay. There we are. So I got the square root of 2, but then I got yelled at, name cosine is not defined. So I can say, well, okay, import square root cosine log. Notice I can give multiple facilities to import from a module by separating them with a comma. And, oh, I see what I did. I accidentally have slog here. So I apparently hit Shift S instead of Control S when I meant to do a save. So Control S saves, and then F5. There we go. So now square root, cosine, and log are all directly available without me having to type a module name. Okay, so those are typical approaches. You can import a module, and then you have to use its name, followed by a dot to access a facility from it. Much more commonly, you import a module and provide an abbreviation. Module names tend to be longer than just 4 characters, and so abbreviations are the normal thing to do. Or if you don't want to use all of a module and you just want to use certain parts of it, then you can say from the module import whatever parts you want, like square root, log, cosine. You can also use from math import and then use a star. Now this is convenient. It imports literally every single thing in the module and makes it available at the top level. But this is also quite dangerous to do, because if you previously had, okay, let me put it this way. Do you know, without having memorized the documentation, all of the names of all of the facilities available in the math module? My answer is no. I don't pretend that I know off the top of my head every single facility that's available in the math module. I know quite a number of them, but I'm sure that I don't know everything. And yet, if I say import, or if I say from math import star, then everything is going to be imported. And the problem for me is, what if I already had some other function that I had defined myself and I had chosen the name SIN? Maybe SIN, in my mind, for my defined function, stands for some input number. Okay, so, well, I should know better than using a name like SIN to stand for some input number, but let's assume that I'm stupid or lazy or both, and I've created a function named SIN that returns some input number. Now, when I say from math import star, my function SIN is going to be overlaid or overwritten or replaced with the math function SIN. So in this case, it's dangerous to do this import star. But let's illustrate that it does work. So I'm going to say from math import star, and then I can execute directly square root, cosine, log, anything that's available in the math library. I can say things like print exponent, which is e to the square root of the sine of pi. Okay, pi is another facility that's defined in the math module, and it's approximately 3.141592653 blah blah blah. It is the value of pi out to the 16 or so digits that can be stored in a float. It's not possible for any irrational number to be stored exactly accurately in a computer, okay, because the computer can only store a finite amount of bits to represent any given number. So pi is available to me from math, and let's analyze this final print statement. Okay, so pi is pi. Sine of pi if you've done a bunch of math or physics or engineering or chemistry or things of that kind, you may immediately know that sine of pi is 0. If you don't know that sine of pi is 0, just take my word for it. Well, the square root of 0 ought to be 0, and then e to the 0 ought to be 1, right? So e to the 0 power should be 1. Let's see what we get when we run this. And, okay, so here's the value of pi, stored out to as many digits as possible. And here's the value that we wanted to be 1. And it's kind of close to 1. But it does have this cumulative round-off error that occurs when you're doing floating point computations on, in this case, values like pi. Because the value for pi is never going to be exact. And as you do increasing nested operations on this value of pi, the round-off error gets worse and worse and worse and worse at every level. Hopefully, you'll have some additional logic in here that says, oh, well, let's just chop off any digits that happen to be starting from the 7th digit or the 8th digit after the decimal point. Let's just, we know that there's going to be some garbage out there, so let's just truncate those. And then we'll have our value of exactly equal to 1. But if you are not aware of that and you're doing important calculations on tiny data sets or financially sensitive or medically sensitive data sets, you might find yourself assuming that certain numbers are important and should be paid attention to, when in fact those numbers are the result of this kind of round-off error. So that's something to be aware of. Okay, so that's modules. Math is one of the most commonly used modules. I simply recommend not doing this thing, from math import star. Just stay away from that so that you don't accidentally destroy pre-existing things that you have defined yourself, called pi or sine or square root or what have you. Okie doke, so that gets us to the conclusion of 3.2, and we have a little lab that will give you some more practice with defining and calling functions with various numbers of arguments, as well as using modules. All right, so signing off until next time.